So let's work example 7 in the book. It says, a rod of length L has a uniform positive charge per unit length lambda and a total charge of Q. Calculate the electric field at a point P that is located along the long axis of the rod and a distance A from one end. So let's draw a picture of this. So here's what's given. And we've got, here's our y direction, which is really not relevant to this problem. And here's x. And what I'm going to do is I've got a rod of some length, and I'm going to say this has a length of L. And it's got a certain total charge on it of Q. And so we've spread this charge uniformly across this length. And we want to know what is, and we decided to put the origin there, what is the electric field at this point right here? Now think about this in terms of the electric field, what electric fields do. Electric fields apply forces to charged particles. And we put a test charge there. So I'm going to put a test charge right here. I'll put a little Q naught. Now, what did I say was true about test charges? They are always, what kind of charge do they have? They're always positive. You have to, I mean, you wouldn't say, oh, well, let's make the test charge negative this time and look at the electric field. No, that would be very, very confusing. Test charges, by definition of what a test charge does, is always positive. So if I put a positive charge here, look at these positive charges. What are they going to do? Positive charges repel. So they're going to push this guy to the left. So there's my electric field. It's the force on this test charge, pushing it to the left, divided by the test charge. Force divided by charge is electric field. Okay? And then we also said that, well, we're going to make this distance A. It's a distance A from here. And we want to know, what is this? And here's the thing, and here's why we're going to have to use calculus to do this. Okay, well, actually, what are we trying to find? We're trying to find E at point P. So here's point P. We have to use calculus to do this because, look, this chunk of charge is quite close. So the electric field it contributes at this point in space is quite strong. Whereas this chunk of charge over here is much further away, so it doesn't contribute nearly as much electric field, and so you have to sum them all up. So, well, we have a basic equation for figuring out electric fields for continuous charge distributions. And that basic equation is E is equal to the integral of K dq over R squared. And again, this is in the video, so if you haven't watched it yet, make sure you get caught up. And when we integrate, oh, in the r hat direction, I have to give it a direction. Oh, there goes my book. So what you have to do whenever we integrate in this class is you have to apply this general thing to the specific situation that we're dealing with. So here, well, there's no r, we don't need an r, what we need is x. And so E is going to be equal to, and the K, That's the electric constant, right? That's that 8.99 times 10 to the 9 thing. And then, so we're going to, what we need to do is get Q and R in terms of the same thing, or we won't be able to integrate. Now R, our distance from our charge to our point in space, or I'm sorry, from our origin, which is where our point is, to the location of the charge in space, that's just all along the x-axis. So we're just going to make it x. So this is going to be over x squared. So we need to get dq now in terms of x. And so whenever we do that, we're going to use a charge density. Now look at this is along a line. So we're going to use a linear charge density. We're going to say that dq, a little chunk of charge, is going to be equal to the charge density per unit length, lambda, and that's the linear charge density, how much charge you have per unit length, times a little tiny length. A little tiny length is dx. And now what is lambda, though? We can get lambda in terms of the given quantities. It said in the problem this charge, Q, is spread out evenly over this. So the charge per unit length is just the charge divided by the length. So this is Q over L, that's what lambda is, times dx. So now I can substitute this for dq right in there. So I'm going to say this is Q over L dx. Now I have to substitute in for the r hat. Well, I know what direction my electric field is going to be. It's going to, all of these are going to contribute electric field to the left. So I'm just going to say negative I hat direction. I'm just going to make the results of this the negative I hat direction. Now, in order to evaluate this, though, I need a starting place and an ending place. Now, here's my origin. I'm going to look, I'm going to go across here, and there's no charge, there's no charge, there's no charge, there's no charge. Okay, then I get here, there's charge right here. And that's when we're going to start integrating. So we're going to start integrating at A, and then we're going to keep integrating, keep integrating, keep integrating, keep integrating, and so on until we get all the way out here. Well, how far is that from, how far is this from my origin? A plus L. And now I can integrate. Let's clean it up a little bit. All this constant stuff can come out. So this is Q over KL. I'm sorry, it's KQ over L. And then we have, to make it easier to integrate, I'm going to go, this is x to the negative 2 power, because it's 1 over x squared, times dx, and we're going to go from A to A plus L. Now, I'm going to evaluate the integral. And this is x to the negative 1 divided by negative 1. Okay? Just use the power rule. And we're going to evaluate this guy from A to A plus L. So let's put in, let's take this negative out here, negative KQ over L. And then we'll put in A plus L. And then we're going to put in A. And we get, doing this right? What am I doing? This negative sign thing is, I dropped my book, so I lost my place. All right, so E is equal to negative KQ over L, and then A minus, this is just L, and yes. That's what I'm doing wrong. Thank you. I was just testing you. All right. So yeah, this should, and that's why this negative sign wasn't working out. This is, thank you, this is X, 1 over X. So this is 1 over A plus L minus 1 over A. Thank you, thank you, thank you, thank you. Because I could tell this was going badly. All right, so we need to combine these together. So let's, this will be A minus A plus L. That's why the negative, that's where the negative sign will go away. And then over A times A plus L. Did I do that right? Just have a common denominator. And so what we get, and this is in the negative I hat direction. And so when I clean this up, I get A minus A. So you get negative KQ over L times, and this is going to be negative L over A times A plus L. In the negative I hat direction. And here we have the negative signs cancel out. And that's why I knew what I knew that I'd screwed up, because I wasn't canceling that negative out. So that goes away. This L goes away. And we're left with our final answer. The electric field is equal to KQ over A times A plus L in the negative I hat direction. Okay? And one thing here's a great way to check your answer when you go through all this, because it is easy to make a mistake, as I did. Look at it from a dimensional point of view. Does this turn out to have units of newtons per coulomb? Well, let's take a look. What are the units for K? Newton meter squared per coulomb squared. What about for Q? Coulombs. And what are the units for A times A plus L? Meter squared. Meter squared cancels. Coulomb cancels with the coulomb squared. I'm left with newtons per coulomb. Voila. It's a great way to check your work when you're doing a lot of mathematical analysis and you're, swinging stuff around, you're integrating, you're doing whatever. So let's do the whole thing here. That is example 7. That is all.